Hey there! If you want to study deep reinforcement learning, don't go anywhere. You're in the right place. Yes, this video is finally published. So first thing first, I want to present my apologies for two things. The first is that I'm late. A2C was normally published 1 month ago, but I canceled the publication because the first version of the article was not really good. In fact, I struggled a lot when I wrote A2C and PPO article about how to explain it simply. Then I struggled a lot in implementing A2C and PPO for a simple reason. In the beginning, I began to implement the simplest version possible, and I think it's a good advice to do like that. So I implemented an A2C agent that learns to play card pool with one environment and one A2C agent. I've done the same thing for PPO. But then I wanted, to add complexity, because if I want to train a Sonic the Hedgehog agent, I need to have a much more powerful architecture. So I used OpenAI Baseline, which is a fantastic repository, but they are very complex because they are very powerful. So I spent a lot of time to study each part of the code to understand the logic behind this code. And finally, I spent a lot of time to train these two agents, because as I said in the former video, I wanted to train from the beginning to the end. So training it to the beginning to the end took a long time and took a lot of experiments. In fact, I spent about 2 weeks to train these two agents because of experimenting, changing the hyperparameters, etc., etc. So it was a very tedious work, but it was really interesting. So that's why I'm late, and I'm sorry for that. The second point is that last time I will implement an agent that will be able to play Outrun. I spoke too fast. I thought that Outrun and Michael Jackson Moonwalker were already implemented in OpenAI Retro Library, which is not the case. So I decided to use Sonic the Hedgehog, which is not bad. Michael Jackson, bad. Anyway. So remember that since the beginning of the course, we studied two reinforcement learning methods. The first was value-based method. For instance, Q-learning, deep Q-learning, and improvement in deep Q-learning. In this method, what we do, we learn a value function that will map for each state action pair a value. Thanks to these values, we will be able to decide what action to take for each state. So this works well when we have a finite set of action. The second was policy-based method, such as reinforce with policy gradient. In policy-based method, we want to directly optimize the policy function without worrying about a value function. In this case, it works well when we have a continuous set of action and when we have a stochastic policy. The problem was how to say if the policy is good or not. To do that, we use what we call the policy score function, which is the total cumulative reward of an episode. So in this case, we are in situation of Monte Carlo. But both of these methods have big drawbacks. That's why today we'll use a hybrid method called actor critic. In actor critic, we'll have two networks. The first that control how the agent behave, the actor, a policy method, and the second will tell us if the action taken was good or not, which is the critic, a value-based method. Mastering this architecture, A2C, is essential to be able to implement state-of-the-art algorithms such as PPO, because PPO is built on A2C. So that's why, first, you need to understand how works A2C. And to do that, you need to read my article. The link is in the description below. Then, today, we'll implement an A2C agent that is able to play Sonic the Hedgehog. So you ready? Let's implement it.
Okay, you're ready to go. I've written down the basic commands so that anyone can understand them.
Homer, bring that back in the house.
Fine.
Okay, so first thing first, I want to present my apologies because normally behind me there was an incrustation, but because I use the webcam of my computer and not my camera, the quality is not good enough to make incrustation. So there will be the green screen behind me, sorry. for that. And the second thing is that I'm currently filming this video not in my apartment in Lyon, but in my parents' home in countryside of France. And the problem is that my neighbor is a farmer, so he's currently using his tractor. Moreover, there's a lot of birds that makes a lot of noise in front of my window. So that's nice because that's the sound of the nature, but that's less nice when you want to make a video. So I'm sorry for that. I will try to reduce the noise in the post-process thing. Okay, so we can begin. So first of all, I want to explain how the code is structured. So there is 5 files. So the first is Sonic environment. In the Sonic environment file, we will handle everything that is about the environment. So the preprocessing, the one-hot coding of the action, the reward scalar, etc., etc. Create the vector of environments, because remember that because in A2C we want to create multiple instances of environment, and to create multiple instances of environment using OpenAI retro library, we need to put them in vectors, in a vector that will contain every version of our environment. And because we use Sonic the Hedgehog, in our case, each environment will have a different level, but we'll explain that after. So the second file is architecture.py that contains the network, the architecture, the layers. So in our case, the A2C architecture. Then we have the model file. So the model file is really important because it contains a lot of things. First of all, it contains the model object. And in this model object is used to generate the step model, the train model, the training function, and some useful trainings such as save and load, to save and load the weights. Then there is a runner object, and the runner object in fact is used to generate mini batches of experiences. And finally we have the learn function that will handle the whole A2C training process. Okay? And finally we have 2 files. So the first agent is used if you want to train the agent, and the second play is used if you want to see your agent training. So that's pretty straightforward. Okay? So we can dive on the first step. So the first step is downloading Sonic the Hedgehog. So here I have a little bad news, is that you must buy it legally on Steam. This is not a joke. In fact, you can't use a free ROM version of Sonic because it will not work. You need to buy it legally on Steam. So yes, you will need to buy $5 for a game made in 1991. But that's like, we don't have a choice, so that's life. And so you download that on Steam, and then you follow the quick start part of the OpenAI retro contest. So when I say follow quick start part, it's that part in that where you will import the ROM into the OpenAI retro library. Okay, so here you follow that. In fact, I will not dive on that because that's not the code. It's pretty straightforward to do. Okay. So now we can dive on the step 2. So the step 2 is where we will build all the elements we need for our environment in Sonic environment. And it's fundamental to make things good here. Because if there is a bug in the environment, you can make the best A2C agent you want, it will not work. So making everything work in the environment part is fundamental. Okay? So let's dive on the code. So one thing first, a big part of this code is taken from the Aborgi, I hope that I pronounce it well, Aborgi Fantastic Implementation. So Aborgi is one of the 3 people who won the OpenAI Retro Contest, and he made a fantastic implementation. So I put the link of this implementation in the description below. Okay, so what I wanted to say about this part of the code, so as I said, is the part that will handle everything about the environment. And the first thing important to say is that we import frame stack. So remember that last time I said that to handle temporal dependencies, we have 2 kind of thing. Because remember that if we just give a frame, let's think about the game of Pong. If we just give our agent a frame, it will not see if the ball is going left or right, because there is no movement in one frame. So the idea was to say we stack 4 frames, and thanks to the 4 frames, it will see where the ball is going. Okay, so that's we call temporal dependencies. So spatial dependencies, sorry. So the problem is that I said last time that we can use framing stack or using LSTM, okay? But it's funny because when I studied the code implemented by the people who won OpenAI Retro Contest, both used stacking frames instead of using LSTM. I think it's because, first of all, frame stacking is much easier, and second of all, LSTM don't is not quite perfect to be used today. And personally, I prefer FrameStack because FrameStack is much easier and it reduces, in fact, complexity. And it's really important because our agent is already complex, so we don't need to add complexity to add complexity. Okay, so another thing is that this time we use CV2, which is OpenCV library. It's a very good library to handle images, transform them, etc. So let's begin. So our first class is to preprocess the frame. So here is pretty straightforward. The first thing that we do is that we set the frame to gray because colors does not add any information. So in our case, we use CV2, so RGB to gray. And then we resize the frame to 96 by 96 by 1. Okay, so here it's pretty straightforward. Then an important class, which is action discretizer. So this class was a little bit hard to me because first I didn't understood what this function was doing, okay? Because there was not a lot of comments in the code. So when you face this kind of problem, you know, when you don't understand what a function is doing, two advice. The first is before trying to understand the whole idea of the function, try to analyze each line of the code inside that function. And then the second idea is try to put some inputs in this function and see what are the output to see what the function is doing, okay? So here, in fact, is really simple, sorry. What is doing this action is that, let's take an example. In fact, it will transform for all action, if we transform all action into a vector, and inside of this vector there will be 12 elements. 12 elements is the 12 buttons, and the 12 buttons will be false except the button that is pressed. So for instance, let's say left, the left action. When you do left action, it means that you press the button left. So what we do, we say that left action is equal to a vector of false, except for the left button, which is true because it's pressed. And the left button is, I think, is number 7 in our list. 1, 0, 1. Remember that it begins in 0, 0, 1, 2, 3, 4, 5. No, 6. 6, sorry. So it's number 6. And that, in fact, it will output an array of vector. And in fact, it's what encoding, to be simple, is what encoding. So it means that we will output for each action a vector where the elements that are true are buttons that are pressed. Okay? So that's only that, in fact. This big function is only that. So then we have reward scaler. So reward scaler is normally used to bring rewards to a reasonable scale for PPO, but we can also use an A2C. In fact, this function just takes the rewards and multiply by 0.01. Okay? Then we have a very important formula, a very important class. This class is allow backtracking. In fact, something important to consider here is that Sonic the Hedgehog is not, a linear environment. When I say linear environment, I want to say that it's not, like Super Mario Bros, for instance, where you have a beginning point, an ending point, and you go straight to the right. Sometimes in Sonic, as you can see here, you see, for instance, that we are in front of the wall. Normally we can break the wall, but let's say we can't break this wall, okay? Because here there is a secret in the real game, but let's say that it's a concrete wall. We can't go here. The idea of the function that we called allow backtracking, as is written, it's to help our agent to not be discouraged too heavily from exploring backwards if it's stuck. So in this case, it's stuck. If we didn't have this function, we have the risk that our agent only tried to go right, even if there is a wall, and didn't try to go left, to go back, to try another path. Okay? So this is this function. And finally, we have the make environment function. So the make environment will create the environment. So first, we have a dictionary. This dictionary is composed of all the levels in our games. So we can see here, they are randomized, so they are not in the game order. Okay? And then here we create the environment. So a quick thing is that we don't use OpenAI Retro, normal OpenAI Retro. We use OpenAI retro contest local because it's more suited for Sonic the Hedgehog. Okay. So what we do here, we create the environment. Okay. So for each element in the dictionary. So it depends on the index that you choose. If you choose index 0, it will create the environment with Spring Yard Zone, Act 3, etc., etc. Okay. So then we build the action array using action discretizer. We scale the rewards. We preprocess the frame, and finally we stack the 4 frames. Okay. And we allow backtracking. Okay. So what we can see here, we create some different function, make train 0, make train 1, etc. In fact, this function call the make environment function with, for instance, here the index 0. So the first level here. Then the train function, make train function 1 will call index 1, etc., etc. Okay, so we've just finished to implement this very important part, which is everything that handles the environments. Okay, so now we can dive on the architecture. So let's begin with architecture. So first of all, we import this function that's called make PD type. In fact, it's make probability distribution type that selects the probability distribution over action. Remember why? Because remember that we are our actor is a policy-based method, and as consequence is we train a stochastic policy. So here, what we've done something which is better that we because in the past I always copy paste. You know, when I create a convolutional network, I always copy paste. But here is better. In fact, because we use a lot of time convolutional layer, it's better to create a function that will instantiate, that will create a new convolutional. So we create a function to create convolutional layer. We create a function to create fully connected layer. Okay, and then here we begin to create our architecture. So the first thing that we do here is that we call the function make PD type that will select, given our action space, what is the probability distribution over our action. So in fact, here, so as I said, it will select what probability distribution type. So we will use to distribute action in our stochastic policy. So in our case, we are in situation of a diagonal Gaussian probability distribution type. So we also call that diagonal Gaussian, aka 3D normal distribution. So I think I have the picture here. Okay, it's like that. So it's a 3D normal distribution. Okay. And then here we begin to create a model. So this is the illustration of our model. We have a CNN, then we flatten the CNN, we have a fully connected layer, and then we have 2 streams. We have one fully connected layer for the actor, and one fully connected layer for the critic. So something important to consider here is that we will not create CNN for actor and then CNN for critic. It's not efficient to do that. So what we prefer to do is to share this part. So this part is shared between actor and critic. And then we separate into 2 streams, actor and critic. Okay? So let's see that in the code. Okay, so here we create 3 convolutional layer for spatial dependencies. Okay, as I said, temporal dependencies is handled by stacking frames. So then we have one fully connected. So we flatten the output of the last convolutional layer, because if we don't flatten, we can't put it into a fully connected layer. So then we pass it through a fully connected layer, which is common to the value and the policy. So it's the last layer before separate into 2 streams. Then we have one fully connected layer for our value function that will calculate the value of the state. And here we have, first thing we have what we call, so it's a this create fully connected layer that return a probability distribution over action. So it's what we call self probability distribution, and our policy logits PI. Okay, so this function here will create, as I said, a fully connected layer and will output 2 things: the logits, so what we call self PI, and the probability distribution over action, self PD. And the final thing that we will do is here, we'll do directly in the architecture. Remember in the former code, when we want to take an action randomly, So, take an action from the distribution randomly. You know, we do that outside the architecture, but here they prefer to do that inside, so we do that inside. So we call the function sample that in fact will return an action, because remember a simple thing where is stochastic policy. So something important to consider is that we don't always take the same action. You know, in value base, we always take the same action. We take the action with the highest value. In stochastic policy, so in policy base, in stochastic policy, in our case, we don't always take the same action. Let's say we have two actions. We have an action with 70% of probability and an action with 30% probability. It means that 3 times of 10 will take right. 7 times of 10 will take left. Okay? So that's why we use sample. And oh yes, a quick thing about self-initial states. We created it because if we don't create this variable, the baseline will not work. In fact, initial state I think is used when you use LSTM, etc. So don't care about that, but just put that in your code, because if you don't put that in your code, you will have an error message. Okay, so that's why we put none to initial state. So there is no use to that. And finally, we create 3 functions that we'll use during the training, during the sampling, etc. So first of all is step. Step returns the action and the value. We have the function value that will only return the value of the state. And finally, a function that only output an action to take. Okay? So here we just implemented a simple but powerful architecture. So now what's important is to work on the model file. So as I said, model file, we have 3 important things: the model object, the runner object, and the learn function. So let's begin. Okay, so we begin with the class model. Okay, so as I said, model is used to generate the step model and the train model, and to create the train function that we'll use to training part. So maybe I will look in my article. Okay, let me find. Okay, as I said, we have 2 models. We have the step model that we will use to create a batch of experiences, and then the train model to train the model. And then when the model is trained, we update the weight of the step model. Okay, so that's why I said in the model object we create 2 models: the step model to create an experience batch, and the train model to train the model. Okay, so let's go back to the implementation. So it's pretty straightforward. In fact, here we create the placeholder, so for action, for advantage, reward, and learning rate. And here we initialize the 2 models. Okay, so the step model. So the step model will only take 1 step at a time for each environment. So let's say you have 10 environments, it will take 1 step for each environment. So that's why here we have 1 of number of steps. On the other hand, the train model for training will take number of environment by number of steps. So in our case, we do 2048 steps, and let's say we have 10 environments, it will be 20,480 sorry, 480 steps. Okay, I'm not really good at math. And then we calculate the loss. So calculating the loss, in fact, we can separate in 3 things: policy loss, value loss, and entropy. Entropy is used to improve the exploration. I will put the paper that explains that in the link in the description below. It's a very good paper, by the way. And so we want to calculate the loss. So remember that to calculate the policy loss is the same thing that calculating the policy loss in the gradients, but instead of using by multiply by rewards, we multiply by advantage. So here, in fact, the policy loss is 1 divided by n by the sum of advantage by the negative of the log of policy. Okay, so, and then we have the value loss. The value loss is just the mean square error between the difference between our bootstrap value and our value, and our predicted value. Okay, and the total loss, in fact, is policy gradient loss minus entropy by entropy coefficient plus value loss by value coefficient. Okay, so when we are calculating this loss, what we can do is first is to update the parameters using loss. So here we find the trainable variables, and then we calculate the gradients, and we apply these gradients in our model. Okay, and remember, because we have two models, so step model, train model, we must apply that in both models. Okay. So then we create a train function. So this train function is pretty straightforward. First of all, we calculate advantage. So we use returns minus values. So why? Because of that. So remember that returns, those I have here. No, I have here. Okay. So returns is this part. Rewards plus gamma by value of the next state. We call that returns. And in fact, so because we have returns, we need to subtract by value of the state to create the TD error. TD error is the estimation of our advantage. Okay, so that's why we have that line. Okay, so then we create the feed dictionary that we'll use to feed our train model. So the input will be the states, the action, the advantage, the return. The return, in fact, return, as I said, this reward plus gamma or value in the next state is what we call the bootstrap of the value, because it's the estimation of the real value. And finally, the learning rate. And then it returns the policy loss, value loss, and policy entropy. Okay? And these two functions is just function that save the model and load the model. Okay, so it's simple thing. They call saver, and they save or they load, they restore the weights. Okay, so now let's speak about the runner. So runner is a really important element in this architecture because it's the part that we'll use to generate mini batches of experiences. Okay, so it's also relatively pretty straightforward. So we create this function run. We create a list that are empty. So obs, action, reward, value done. That we will inside we will put the batch of experiences. So we create a loop. So for n in range number of steps. So in our case 2048. We get the action and the values using the step. You know, the step is a function that we define as the architecture. In this step, we put observation. So we put downs, but don't think about that. It's just because in the OpenAI baseline we put two another thing, and I think it's because also for LSTM extra. But don't think about that. There is no. It's not useful to put self downs, but we need to put it. So in fact, in step we put observation. So and we will output the action to take and the value. And you can say, but wait, why we can put observation if observation is empty? And in fact, because we use abstract environment runner, okay, this object called abstract environment runner, and this object abstract environment runner already run the environment reset, so it returns already returns observation. Okay. So here then we append the observation into the mini batch observation, we append the action, the values, the downs, etc. And then we take action in the environment and look at the result. So result are new states, rewards, and downs. Okay, and then we append the rewards. When we finish the loop, as always, we transform each of this list into NumPy array because it will be more useful to feed NumPy array in our network. Okay. So here something a little bit tricky. Okay, but I will try to explain it simply. So it's what we call the generalized advantage estimation. So instead of calculating simply the advantage, we use this formula, which is considered as better to calculate the advantage. Okay. So I will put the link of the paper in the description below also. It's a very good paper, a little bit hard to read, but it's very powerful. Okay, just a quick thing about the difference between returns and advantage. Returns is just reward plus gamma by value of the next state. In fact, returns is what we call the bootstrap value. Remember that when we calculate the value error, we calculate our predicted value minus the real value, but we don't have the real value because if we had the real value, we didn't need a neural network. And because we don't have the real value, remember, we bootstrap it. So in fact, we say that the real value is equal to reward plus gamma by the value of the next state. And returns is that. And that's why you can ask here, but why we say that return is equal to advantage plus values? Because I said returns is that. Okay? But advantage is the same thing minus value of the states. And because we want to have returns, we just need to add value of the state to cancel the subtraction. Okay, so it's pretty straightforward. So now I want to explain the generalized advantage estimation. First thing first, what is next non-terminal? It's pretty straightforward. If we are in a situation where we are not done, next non-terminal will be equal to 1. Else, next non-terminal will be equal to 0. Why? Because when we will calculate this formula, we know that if we are in a state that it's a final state, we will not have value of the next state. So here will be equal to 0. So the advantage will only equal to reward minus the value of the state. Okay? So what we've done here is if next non-terminal is equal to 0, it means that we are in a situation of last state. In fact, this gamma by value of the next state by next non-terminal will be equal to 0, and the delta will only equal to, aka the TD error, we only equal to reward of the state, of state and action minus value of the state. Okay? Else it will be equal to this entire formula. So it's just a practical way to avoid, create a loop to say if it's done, else extra, as we've done, in the DeepQN implementation. So here is a better way to do to handle this problem. So to calculate advantage, it's a little bit different. In fact, because we are in this loop, and it means that we have in reversed order. So it means that we begin in the last step and we finish in the first step. So let's say we have 10 steps to be simple. So the advantage of the step 10 is equal to delta plus gamma by lambda by next non-terminal by last general advantage estimation lambda, in this case 0 because we define here. So all of that will be equal to 0, and our advantage will only equal to delta, aka TD error. Okay, so it will only equal to that. Okay, then the step number 9. So let's say, for instance, that this will be equal to 2, to be simple. It means that next time the last general advantage lambda is equal to 2. So the step number 9 will be equal to delta. So 2 is on TD error, let's say 1, plus gamma by lambda by last general advantage lambda. So it means plus by 0.99 by lambda, I think lambda is 0.05. Let's verify. No, sorry, 0.25. So let's calculate that. Okay, so I said 0.99. So if we go back in the calculation, sorry, okay, so as I said, we said that the advantage of step number 10 was 2. Okay, so we said that, and let's say that here the TD error is 1. So we will say 1, so delta plus gamma, so gamma discount rate is equal to 0.99 plus, but iPad are really not practical, but kind of tough, by, as I said, lambda, so is 0.95. By, so it's non-terminal, so by 1. And by last, okay, so this will be equal to 2.881. Okay, so advantage for the step number 9 is 2.881. So it can seem a little bit tedious, but in fact the idea is that each advantage in a series of steps are a little bit correlated. So that's why we use that kind of calculation. Okay. For more information about the calculation, if you want to see that the formula in mathematical way, there is the paper in the description below. Okay, so we're calculating the advantage using the generalized advantage estimation. So then we calculate, as I said, the return, and I say the returns is equal to NB advantage plus MB values, as explained above. And then here we reshape using this function that reshape swap and flatten the axes 0 and 1. And so we reshape our NumPy array of MB observation, action, returns, and values. Okay? Okay, so here we'll implement the learning function. I will explain in two parts. First, I will explain the big picture, and then I will dive on this explanation about the number of optimization approach, number of mini batches. So, to be simple, learning function combine all the elements to train our agent. Okay? So, it's relatively simple. We have here, we instantiate the model that creates the step model and the train model. We instantiate the runner object, and then we start the training. So for update in range, in our case, I think it was 3 million steps. So what we do is get mini batches of experiences using the function run of the runner object. Then here we train, so I will explain after why we train like that. So we train, we have the loss value, okay? And then what we do here, we calculate also the FPS, so the frame per second, to see how fast our computer can handle the training of this agent, okay? And then what we do, we'll print into the logger the different elements we need to track. So first of all, we calculate what we call the explain variance. So to be simple, explain variance will tell us if our value function, if our critic predict better than if we predicted 0. So to be simple, if explain variance is equal to 0, it means that it is not useful at all. The value not predicted correctly, the value, okay? If the explain variance is equal to 1, it means that our critic evaluate perfectly the real value, okay? And if the explained variance is below 0, it means that it's worse than just predicted value. It means that we are in a case of overfitting, and in this case, we must choose the hyperparameters. So the idea is that, during our training is that our explained variance continue to go closer to 1. Okay? Then we write another element that we want to track, the number of updates, the total time steps, the FPS, policy loss, policy entropy, value loss, and time elapsed. Okay? And then we save the model at each 10 number of updates, we save the model. Okay? So now I want to dive about the training. Something important to consider. Let's say we have 10 environments, and we have 4096 steps for each environment. It means that we want to feed our network 40,960 steps, which is really huge, and we can run out of memory. So the idea is to use this batch size, which is 40,960 steps, divided into number of mini batches, so create mini batches of training, and then here, what we do here during the training, in fact, we create the indices array, we randomize the experiences, so it means we take this huge batch of 40,000 and we randomize the experiences to avoid correlation, remember during deep Q learning, because we're in a situation of TD learning, don't forget that, so to avoid all the problem of correlation, etc. So we randomize the experiences, and then we took 4 times a mini batch of, let's say for instance, the number of our batch train size is 6,000. We take 4 times 6,000 and we train 4 times our network with 6,000 batch of experiences. So to be simple, we can't feed 4,960 step into our network. So what we do, we divide that number into a number of mini batches, and then we randomize our experiences and take 4 times. If we define 4 number of optimizer approach, we take 4 times a number of mini batches and we train with that. So we just do mini batching, in fact, as we do always with network, okay? And it's important to randomize, by the way, because as I said, we are in a situation of TD learning, and remember my article about deep Q learning, about the problem of having correlated states, that can train to a bad training and overfitting. Okay, so we finished to implement the learning function. So, and now we'll implement the agent.py, which is a file that you call when you want to train our agent. So first of all, we'll import subproc vector environment, which create a vector of n environment to run them simultaneously. Because OpenAI Retro, we can't run multiple environments at the same time. So what was we need to use subproc vector environment. In fact, it will take all the instances of environment, put them in a vector, and it will be very useful to run a different environment simultaneously. Because remember that, as I said in the beginning of, I said in the course, and I said in this video, why we do in fact, we have a multiple series of environments in different levels, because having different levels helps our agent to generalize better, to avoid overfitting, so to be smarter in fact than just having one level, because if you have multiple level, it will see multiple obstacles, multiple things, etc. So we use subproc vectors environment that will help us to create a vector of n environments. Okay. So then what we do here, in fact, we allow our GPU memory growth. In fact, we say to TensorFlow, you can use our GPU and you can grow the demand for GPU during the training. Okay? And then so we create the session. Okay? And we call the learn function with all the hyperparameters that we need. So here we have the subproc vector environments. In fact, so subproc vector environment is what we import here, and inside we call the function we want to create our environment. So make train 0. So make train 0, I think I didn't explain in the beginning, but it's relatively simple. In fact, make train 0 here, what we can see here, in fact, call the first level, so Spring Yard Zone Act 3, sorry. Sometimes my French go backs. Make train 1, so here we call that, etc. So in fact, each function call one of the levels. So what we do in the agent, in fact, we create this vectorized vector that will contain the environment. So that will contain, in our case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 environments. Okay. That's number of steps. So I made a mistake. I said that we use 4096 steps. So in our case, we don't use the 4096 steps, but 2048 steps. Okay. Then the number of time steps for the training, the gamma, so discounting rate, the lambda that we use to generalize advantage estimation, the value coefficient, the entropy coefficient, the learning rate, and the max grad norm. In fact, max grad norm, I didn't spoke about that before, but in fact, it's used to have a maximum gradient, to avoid, big movements during the gradients. And finally, the log interval. So this say only print in the log, so in our console, each 10 n updates. Okay. So with all that in mind, we created an A2C agent, and as you saw, finally, when you see the code without comments, etc., it can be really hard because the code is not really really simple to handle. But as we walk step by step with different logic, first of all, implement the element for Sonic environment, then implement the architecture, then implement the model, then implement the runner, etc. I hope you understand how works A2C. And I think that it's really important to separate each element of the code, because it will help you to really see the logic. For instance, if you want to modify something, if for instance you want to modify the runner, you can modify in the model file directly. You don't need to search in the one only file with a lot of code. So it's better to see, it's better to understand the code, because we separate each logic. We separate the architecture to the model, to the play function, etc., etc. So I really hope that this video helps you to really understand how it works. Don't forget that if you have some problem of understanding, go back to the video, make pause, because it's important, I think. And a thing really important, don't just take the code and just read the code, write by hand, And another thing, try to modify it, because this code is not perfect. It can be improved, you can add more elements in the architecture, you can change hyperparameters, etc. Try things, experiment, and have fun. So that's all for today. You've just implemented an agent that is able to play a very complex environment, which is Sonic the Hedgehog. That's fantastic. You can see in the testing set that our agent is not able to understand the loop. But something important to consider is that our agent was trained for 10 hours, and during these 10 hours, he learned so much. If you see the difference between the first epoch and the last epoch, you see a big improvement. First of all, in the first epoch, our agent played randomly. In the last epoch, our agent learns that he must go to the right, he understands how to jump, how to run, etc. And something important I want to say is that during the training, our agent had a lot of problems with slopes. You know, there is some slopes in the levels. And our agent in the beginning, I think it was during 30 to 80 epoch, he was not able to manage this slope. You know, he jump and he fall, and he don't understand. He jump, and it was really hard to him. But finally, he understood. So something important to consider is that our agent is really smart because he succeeded to overcome each obstacle he found. However, he has a problem with this obstacle. We'll see next time with PPO that we will overcome this obstacle using a more stable architecture, as I said, PPO. So now, I want that you take some time to reflect on all the achievements you made during this course. Remember that the first problem we achieved were simple text problems such as OpenAI Taxi version 2 and Frozen Lake. Then you dived on much more complex problems such as Space Invader and Doom, and now you're able to create an agent that learns to play Sonic the Hedgehog. Sonic the Hedgehog is a very complex environment. Why? Because there is, first, a lot of obstacles. Second, the environment is not linear. But it means that it can have a big wall and you must go back, etc. And it's complicated to an agent to understand that he must go back to change the path. So it's a very complex environment and our agent is able to play it. Next time, we'll show that with PPO is able to finish the episode. So this will be fantastic. And we'll use to do that Sonic the Hedgehog 2 and Sonic the Hedgehog 3. I hope you enjoyed this video. If you have some questions, feedbacks and advices, please write them in comments below. Don't forget to like the video. See you next time. À bientôt. So don't forget to subscribe for more deep reinforcement learning video. And don't forget to like the video. And don't forget to keep learning and stay awesome.